Um, so today I'll speak on the magic of deep reinforcement learning. I'll give the context of why I call it magic, what kind of deep impact it has, and what kind of technologies it uses. Essentially about what kind of recent improvements have happened in deep learning and reinforcement learning that cause this thing to become applied to a lot of the real world problems. So I'll cover the overview of deep learning and reinforcement learning for people who don't have a background. So how many people here knew about deep learning? If I can understand. And reinforcement learning? Okay, that's cool. So I'll give an overview of what is deep learning and what kind of applications it is being used for, and reinforcement learning and why has it become so important and why is it so applicable to a lot of the real world problems. And then I'll delve into the topic of how these two technologies are combined to give the power into what is called deep reinforcement learning, which was basically patented by DeepMind in Google. I'll give some instances of applications of deep Q networks for Atari games, then other techniques like policy gradients, deep DPGs, followed by challenges, conclusions, and some overview of the recent advancements, which is the AlphaGo, which Google brought out, and it became such a wildfire in the industry. These slides are a combination of slides from David Silver's tutorial on deep reinforcement learning and policy optimization methods by people from Berkeley AI Research Labs. So deep learning is basically a representation learning. Essentially, if you have a set of images as input, there are a set of nodes in a neural network which have multiple layers. There are connections across the layers. These layers basically have weights. They are trained, and finally at the end you get a representation of the image. This essentially mimics how your brain or visual cortex works and processes images. Essentially from the raw pixel images you get higher level of abstractions on that image which represent features of that image, namely the edges, the vertices, the smaller objects that it makes out of edges and vertices, and then the higher level objects. So basically if you find there are learned models that Google has put up and other universities have put up, basically where you can have, they have trained how to recognize objects. So you take this model, it's a pre-learned model, it's a neural network of, a convolutional neural network of 12 layers or so, or 14 layers, and it can recognize all multiple types of objects. It can recognize a board, a chair, a cat, a dog, and so forth. So what happens in a deep neural network is that we are given an objective. The objective is what do you want to learn. So basically it's a supervised learning problem. It also handles unsupervised problems, learning problems. But in a supervised learning problem, essentially you tell the network that this is a cat, this is a dog, and so forth, and you train the network over millions of images. So the training data has to be pretty good in size so that you can actually train the network to a sufficient generalization and not necessarily to just overfit. So you are given an objective and the network learns this representation. It is up to you how many layers you set up in that neural network architecture, what kind of activation functions you use at the output of each layer, right? What kind of training algorithms or optimization algorithms you use to train the neural network. And then essentially you train the network over these millions of images, in this case of a convolutional neural network, which I'll give an example after this slide. And it learns a representation, which means the weights are learned in the network, and at every output of each layer of the network, a representation can actually be seen of what the computer has learned, and you can really visualize, and it very similarly mimics of how the visual cortex in the brain represents the different images. The inputs are raw images or as pixels, and it uses minimal domain knowledge. So normally computer vision algorithms in the past, before deep learning came into existence, before convolutional neural networks came into existence, was primarily based on taking the image, having a lot of creativity in building n number of features, and the team or the research group which could actually build a good number of features actually could give a higher accuracy on that particular prediction problem or estimation problem. In this particular case, it's about how what is the right architecture that you make. You don't pretty much tune or build features, the network builds the features by itself. What really matters is what is the choice of algorithms, and people have been looking at different kinds of optimization algorithms that give you the best accuracy of these outputs. So this is what a deep representation is, as I was mentioning. X is a raw input, which is a raw image, for example. It could be text, it could be voice. And then you have these hidden layers, H1, H2, H3 up till Hn. You have an output function Y, and then you have a loss function. From every layer to the next layer, there are a set of weights, W1 to Wn. And these are the weights that is learned by the network when you actually train it with the loss function. So the gradient of the loss function is back propagated using a simple chain rule of differentiation, and that's how the weights get updated. This is the fundamental basis on which the neural networks work. This kind of theory existed for the last 50 years. But what happened in 2007 when Hinton specified a specific way of learning these networks, that's how this became really popular and got applied to real world problems. So you can, in a transformation across the layers or the specific activation functions that you use at the output of every node of the neural network, it can be linear, right? Or it can be a non-linear activation function. So from one layer to the next, it takes simply the output of the first layer, output of the prior layer to the input of the next layer is a linear transformation, and the activation function actually is a non-linear function, which could be a sigmoid function, Tanner function, ReLU, rectified linear units, and so forth. The loss function is something that we tune based upon what kind of image or output that we want to train, and this can be a mean square error or a log likelihood. One uses typical techniques. This is a highly nonlinear function. A highly nonlinear function is able to basically recognize or differentiate and discriminate across various types of images. So one cannot use perfect optimization algorithms and achieve a global minima that converges the network and perfectly recognizes the image. One uses basically approximation methods because these are highly nonlinear optimization problems. And one typical technique you would use is stochastic gradient descent. There are other techniques like Adams and so forth which improve on this and avoid certain problems like the saddle point, which is mentioned in the image over here. So basically there are some multiple variants of the deep neural networks. One is a very, very popular neural network, is a recursive or recurrent neural network rather. In here the weights are shared between the layers. So essentially if you have one hidden layer, the output of the layer typically goes to the next layer. In this case it also goes back to the same layer. So this helps in having a limited amount of memory in a recurrent neural network. In order to recognize images that I was mentioning earlier, one uses convolutional neural networks which have become very popular. They are used for both images as well as videos. And here the weights are shared across the region on which these are applied. So you basically have a filter. A filter essentially takes the raw input image or the raw or the intermediate processed grid from the prior intermediate layer and then applies a convolution operation on there with the same weights and shifts with a certain stride. That gives you the output which goes into the next layer, the input of the next layer. That's what is happening. The W1s that are getting applied over there that essentially lead to the next representation, which is the higher level of abstraction in the convolutional neural network as you move forward through the layers. So what is learning? Learning is basically optimization of a function. Essentially, if you have a neural network and you train it and you see the output, unless it has converged, unless the loss function has gotten reduced in value, which is let's say the mean square error or the log likelihood, unless that has happened, the kind of recognition accuracy that you are going to get will actually be very low. So what you are basically doing is, over this particular optimization function, you are actually solving for the problem. So you have a forward pass in which the images input and block of differentiable computes are calculated. In the backward pass, using the chain rule, the optimization happens. So one particularly interesting networks are recurrent neural networks. In here, essentially, as this diagram shows over here, the links are basically back to the same layer. So the hidden layer essentially feeds itself. The output of the first set of inputs goes essentially back to the same input layer. If you unroll in terms of time, you have a sequence of inputs. Let's say a time series. Let's say a video with a sequence of frames given xt minus 1, xt plus 1 as 3 specific time points. With the same weights, they basically feed into the hidden layer, and then across the unrolling there is a weight w, the matrix w, that essentially is the rollback or feeds into the same hidden layer. So the state of the output from xt minus 1 goes back, which is st minus 1 goes as to st, and that goes to st plus 1, and then also correspondingly you have a certain matrix V through which the output is obtained. So imagine you are doing a time series prediction problem. You are given a vector time series. You can solve it using vector ARIMA. It has limited set of accuracy as you would have seen in practice. But if you actually end up using LSTMs or RNNs, you would get much better accuracy. In the same thing, if you have a video prediction problem, which is a harder problem, because you have much more complications and objects and interdependencies among the objects in the spatial way as well as in the temporal dependencies, then if you use an LSTM, it would have a certain meaningful level of accuracy which a vector ARIMA may not be able to solve at all. So that's what is basically a recurrent neural network. An advancement, which is a very fundamental advancement that happened from RNN, is the LSTM, which are long short-term memory networks. Essentially what happens here is that you have 4 layers in what is called a cell. So as you see the cell over here, so you have the same sequence, which is xt minus 1, xt and xt plus 1. You want to give outputs here labeled as ht minus 1, ht and ht plus 1. Imagine this is a time series prediction problem. You are given an input time series, which is x. You want to have a predicted time series, which is basically h. And here you have this full cell instead of just a simple Tanner connection through the self-looping, which was there in a vanilla RNN. So here what you have basically is basically you save the state of the cell. In that state, how do you propagate? So how do you save the state and how do you propagate to the next layer? Essentially you save this, first of all you say whether you want to forget the state or not, right? So you take what is the current input, what was the past output, right, which is the ht minus 1 over here, right, and then you decide using a sigmoid function how much of that prior state, which is this particular arrow, you want to propagate to the next state of the cell. So essentially first you have a forget operation, and this multiply operation basically says how much of the prior state you want to keep in the next state. Then you basically use an add operation, which is what is my next state that I want to compute. So what you do is basically a plus operation, simple addition, where essentially you compute the next state, which is basically a combination of a Tanner function which depends upon the current input xt and the prior output ht minus 1, and you essentially take the sigmoid function which controls how much of this state you want to propagate further, which is the current state computation. You add whatever you wanted to forget or propagate of the prior state, you take the current state and then you make it go further as the next state. And from this state that you have computed, that you want to keep for this particular time slot, which is xt or time t, you compute what is the output that you want to get out of the system. For example, in a prediction problem at xt, what do you want to output as ht, so that that essentially has the highest accuracy in the time series prediction problem, for example. So essentially what LSTM does, it formalizes the concept, the memory concept of a vanilla RNN through cells and states of the cells, and through basically various matrices. So each of these arrows is a vector operation that is happening. Each of them has weights that goes to the next layer and the next operation. And basically that essentially determines how much of the prior state you want to forget and how much of the prior state you want to remember. So that if you have a sentence in which person X learns French and or it basically stays in France, and then some other text has happened and finally it says what is the language he's going to speak over there in France. If you have to fill it up, the whole dependency of these sequence of words that has gone in, actually for the last answer depends on the first sentence. So that dependency is kind of learned by the system. It forgets the intermediate points. It learns that this particular output, which is French, depends upon the last word of the first sentence. Given that there are a lot of intermediate sentences, it forgets all the intermediate state and it uses that to predict that this should be French because it depends upon France. So essentially that's what is a long short-term memory, right? And it performs really well on the tasks of the application which I just mentioned. So if you have, how many people have seen Google Translate here? So if you just type Google Translate, it will give you like 50 to 100 languages you can translate to other language, right? So what they are basically running behind it is an LSTM. So and more sophistication and heuristics around it as well, but the fundamental technology is an LSTM. So what basically here is this is machine translation. So essentially, as you can see, you have these three inputs. These words are vectors. So these words are converted into binary states or real numbers, a vector of real numbers, each of these. They are fed into this particular LSTM, and this encodes the information. These are encoders, these are decoders, and they will convert this to English, right? So this is one of a very fundamental application that has become very prevalent, and that helps all these industry players to give you lots of applications in all the languages, and that's really becomes very useful in the market. Another application is image question answering. So here basically what you are given is a cat, an input image, and you ask the computer a question, right? So you're given a cat here and you say, what is the color of the cat, right? So the ground truth, obviously it's black, but different algorithms, what they emit essentially is the probability that it is black. So essentially in the output layer, you train it using a softmax function, and you have a node for black, and then it says it emits a probability of 0.55, which is higher than all the other probabilities of all the other colors, and then you basically say, okay, it is actually black. In this case, this works better, which is the LSTM based method, and it can give you a 73% probability that actually it's a black. And then it says, what is the color of the couch? And then again you have these probability emissions. Same thing holds for how many chairs are there, and there are different probabilities in which they answer. How many shells are there, and again there are different probabilities in which the system answers. So if you look at the architecture of this network, basically the image is given through a convolutional neural network, gets converted into features, then it goes through linear transform and gets input to an LSTM. The LSTM sees that as the first input in the sequence, followed by the actual question, which is how many books are there, or what is the color of the cat. And through the sequence translation capability or the long dependencies capability of the LSTM, there is a decoder, and essentially that emits the particular answer in this case, which is 1, 2, or whatever is the particular function or the output on which you train it on, which is essentially a softmax probability function. So this is a very recent work, just a couple of years back, and it shows the power of LSTMs. Video description generation. So now not only now people have become adept at, or the algorithms have become adept at image caption generation, you also can generate description of videos. The accuracy of this is still limited under the agreed on metrics like the Meteor score, but essentially what is happening is that you have a sequence of video frames. So you take a set of video frames, which is the input sequence, and what you output is what is happening over here. So S2VT basically is a sequence to sequence video to text model, which is an LSTM based model, which is shown over here, and this essentially emits out a man is doing stunts on his bike. If it is trained in a certain way so that it outputs something semantically similar to this, which is not very different from this sentence, then still this is going to get a high score if this is actually the ground truth, right? And again in this case you see a video image of zebras, and you have heard of zebras which are walking in the field, right? So these are the correct description that it generates, but here are the relevant but incorrect descriptions, where in this particular image it emits out a small bus running into a building, which is not the case. And again in this case it is emitting something which is relevant to the image, but it is not accurate. There are also other outputs in this particular paper of 2015 where the output is totally different from, it's not even relevant to what is actually happening in the particular video that is being input. So this is still a active research area. And here actually if you see, you have an LSTM layer which basically encodes the particular video sequence as an input, and then essentially that leads to the decoding layer where the sentence gets generated. And as you propagate using the stochastic gradient techniques and other optimization techniques, basically this network learns to emit these kind of sentences. So it's very impressive in all the different applications that you can do. You also have other applications, which there are startups which are now doing content generation, which can be used for marketing. And there are multiple startups which are actually doing content generation, where you give a description of the product and it will generate you a full text of the product, right? Or you give attributes of a hotel. This is a hotel in Bangalore at such and such location, and with such and such features, it's going to give you a very interesting description of the hotel which you would love to read, and it helps you in your SEOs and things like that. So here is another very interesting example for in the area of self-driving cars. So this was a competition which was arranged by Udacity, and the first and third place winners ended up using just RNNs to solve this problem. Here essentially you are given a sequence of video frames of how a car is navigating through a curved road, and what basically you need to figure out are steering angles using sequence to sequence mapping, right? So what people used are essentially LSTMs, which are specialized RNNs, and the input, what they did was they basically did 3D convolution of the image sequence. You get a 3D convolution of how the car navigates through the curves, or actually is going through the curves. And they predicted, other than steering angle, they predicted the speed and the torque as well. So this is what you basically give as a huge number of training sequences, where you have these video frames as input, then you have these particular steering angle, speed and torque, which are supposed to be taken by the car as the training data, and using a sequence length of 10 frames in a particular set, and that's basically they would determine the speed, angle and the torque. So this was deep learning. So deep learning has advanced quite a bit just even in the last 4 years. Forget about the 10 years in which when it got started by Hinton's work in 2007. So another work in parallel that has been going on essentially is reinforcement learning. Reinforcement learning is a much older field and has much deeper mathematical convergence proofs and justifications than deep learning. So reinforcement learning has a lot of advantages. Reinforcement learning basically is very different from the typical supervised and unsupervised learning you have. In deep learning basically, or supervised learning rather, you essentially have a feature vector and you immediately have a label on which you classify. In reinforcement learning, the reward is not given to you immediately. So imagine there is a robot. It goes from a start state to an end state. Intermediate, there are obstacles. Intermediate, there are pits. If it falls in the pit, gets a -100 reward. If it reaches the target, it basically gets a +10 reward. In all the intermediate fields, it gets a very minuscule, minor or negligible kind of a reward, right? So it takes the first step, it has no clue, right? It has no clue what to do. So it takes n steps, goes through a whole curvature of this route. Finally, when it reaches the start state, it realizes, oh, so it finally got a reward. Right? So how do you train such a system? Right? As you would see, this is an optimization problem. You want to have the best policy, which is a set of actions you take across the grids so that it reaches the final state. Right? So that is the kind of problem a reinforcement learning solves. So imagine problems like there is a robot, right? The robot basically needs to do two kinds of things. It needs to walk with its all kinds of motors and equipment, that is mechanical equipment that it has. It has to control the angles and the torque and so forth, and also it has to plan across this. So there are two optimization problems it has to solve. If it takes the step in the wrong way, the robot is going to fall. Other than that, in addition to that, it also has to plan through the whole maze so that it reaches its target, or it can have a target of picking a cup which is lying on this particular table, right? So in all these kind of problems, and there are a huge number of examples which I'm going to show today, you think the robot essentially needs to plan ahead, right? It needs to learn the environment. If the environment is completely given to the robot, the game is very easy in some sense, but still it has to plan on the environment to make the optimal move or the optimal set of actions, which is the policy that the robot decides, right? If the environment is not given to the robot, then the robot has to learn, which is called a model-free reinforcement learning, where the underlying system is not known to the robot. It will explore, it will fail, it will fall, and then finally it's going to learn. So I'm going to show you some interesting videos on that. So what is happening in reinforcement learning? Basically, you have an agent. The agent is the particular robot, or if you see a canonical example, it is humans as we learn all different things in life. And if we are doing things for the first time, we don't understand how this complex system of what careers one should take, or how this complex system of how this particular industry runs. But we try certain things, learn, we fail, and then we build policies, we simulate the models in the mind, we generalize the models, and then we say this is the right way I should have taken, therefore in the next step I will make this move, and then I'll get a reward after some time because I know this actually works, and I've tried by errors and failures that actually it will happen. And more so in startups, right, with a huge probability of failures. So this is an agent. It takes an action. It has the capability of taking an action. If you don't take an action, you will go nowhere, anywhere, right? You are in a static state. So you take an action. The environment is basically something that the agent may not, in a 99.99% of the real life cases, the environment is not known to the agent. So it just learns the environment by experience. The environment gives puts the agent to another state, whatever the agent can observe of the environment, and then the environment also gives a reward. The reward can be finite, infinitesimally small. The reward can finally be a delayed reward. But basically this is the cycle through which an agent goes. So basically there is a sequence of decisions the agent needs to make, and it goes to a certain state transition, analogous to how a robot would move in a grid. Right? So what is basically it has? It has an agent. Each action influences the agent's future state. What action you take now, today, that you are sitting here and watching this particular lecture, tomorrow is going to improve your future state. Your mind will have certain kind of biases, certain kind of learning, certain kind of future thinkings you may want to take based on sitting here and listening to this lecture. The success is measured by a scalar reward signal, and the goal essentially is to select the actions to maximize the future reward. The future reward can be the set of total rewards that you take, or in a typical case, because there is huge uncertainty in the future, the set of actions that you take, you give discounted reward. So you don't get full reward to the future, because you say if you take this set of actions, then you will achieve this reward, but by the time you reach that action, the system state has changed. So you give discounted reward to the future state, as I'll describe in just after this. So reinforcement learning is a very interesting field. It cuts across and gets applied through into computer science, engineering, mathematics, economics, psychology, neuroscience, actually in many other areas. And it basically leverages from machine learning, reward systems, operations research, game theory, optimal control, right, and so forth. So it has again very interesting applications in game theory as well.